Hello, we're going to talk about applying some of these spectral analysis tools to pianos. This is the list of the tools we're going to be talking about. And before we can really get into applying them to pianos, we have to walk before we can run, which means we're going to take a look at how these things are applied to some simple waves. We're going to use the line spectrum, cumulative line spectrum, spectral centroid, and the autocorrelation to three simple waves. That's part one. The first wave would be a simple sine wave, 440 hertz. There's the time domain graph, plotting amplitude versus time in milliseconds. Here the red line denotes a period of 2.27 milliseconds, which corresponds to the reciprocal of 440 hertz. Down here is a longer view over about 13 plus seconds, 13 plus milliseconds, and I got a red line showing 4 periods of the wave. Here's the sound. Okay, let's take a look at the line spectrum, cumulative line spectrum, and the autocorrelation of this simple wave. Here's the line spectrum. We're plotting signal strength against frequency, and at the frequency of 440 hertz there's a peak representing the strength at that frequency. There are no other spikes or lines because there's no other component in this wave except the 440 hertz. Here's the cumulative line spectrum. We're plotting percent accumulated power on this axis, and we're plotting the frequency on this axis, and we move along from left to right along the frequency axis, and as we go left to right we accumulate power, and so we go all the way up to 400 hertz. There's no accumulation because there's no component at 400 hertz or less. At 440 we have our one and only component, which brings us up to 100%, and it stays that way. So the cumulative line spectrum of any wave is going to be a non-decreasing curve. It may be flat, but it's never going to decrease. All right. Let's take a look at the autocorrelation of that sine wave. The autocorrelation is the time it takes for the peaks to arrive at the sensor. For example, in this case, we have peaks at 2.27 milliseconds, double that, triple that, because that's the time at which the peaks would arrive. And we're looking for the first and tallest peak, which occurs right here. This is the reciprocal of 440 hertz. For this simple wave, you get an autocorrelation of 1 at these points, because the sine wave autocorrelates with itself perfectly at these periods. Here, for example, is the autocorrelation from -1 to +1. The autocorrelation always starts out at +1 at 0 lag time, because at 0 lag time you're autocorrelating the signal with itself with no lag. And so it's going to be 1 because it autocorrelates with itself. Okay. Now I'll talk about a slightly more complex wave. This one's going to have a variety of harmonics, 9 of them. Here's the plot of the coefficients in the sine waves, for the sine waves in it, starting out with 440, and then there's one for each harmonic. The coefficients decreased, and then after the 9th harmonic there are no more. So this is a wave with a series of sine waves in it with different frequencies, and the frequencies are harmonics of the lowest frequency, which is 440. Here's the wave structure in time, plotting the amplitude against the time. It has a recurring period of 2.27 milliseconds, which corresponds to the fundamental. And you can see the other wiggles in there, which are a consequence of the other harmonics. Okay, the first sound you heard was the sound of this wave. The second sound was the sound of the single 440 hertz. The first sound was a little bit tinny, at least to me it was, because it has the higher harmonics in it. Here's the line spectrum. You can see I'm plotting signal strength against frequency, and I get a line at each of these harmonics. The strength or the height of the line decreases because there's less power at the higher harmonics. And I'm also showing the spectral centroid, which is the weighted average frequency, and it's weighted by the strengths of the frequencies. So basically you add up all the frequencies multiplied by their powers, and then you divide by the sum of all the powers. This thing occurs at 806 hertz, which is a little bit left of middle on this graph because there's more power down here at the lower frequencies. So the spectral centroid is a fancy name, but it's nothing more than an average frequency weighted by the strength of each frequency. Okay, here's the cumulative line spectrum of the build-up signal. I'm going from left to right, and I'm plotting percent accumulated power. And I'm going to start off at 0, no power at 0, nothing until 440, which we gather about, looks like about 21, maybe 22% of the signal. And we go over to 880, and there's some more, a little bit less, say 18% or so. And then in each harmonic you gather some more power, and then finally the last harmonic at 3960 you gather the last bit of power, which is about, looks like to be 7% of the signal, and then from then on it's 100%. The step size decreases as the frequency increases because in fact you're adding less and less percentage of the power as you increase in frequency. Here's our spectral centroid at 1806. Beg your pardon, probably, yeah, 1806 hertz. Here's the autocorrelation of that built-up wave. Again, it's a simple wave, so we have total autocorrelation at 2.27 milliseconds. And this is telling us that the pitch of this wave is 440 hertz. And of course it repeats because it's going to autocorrelate at the multiples of the period of this signal. Put it on the same graph. Okay, here's the line spectrum that we've seen, and here's the cumulative line spectrum, both plotted against frequency. This is signal strength at the frequency. This is the accumulated power as we go along in frequency. Okay, now one more signal. This signal is going to be just the converse of the other one. We're going to start out with a small component at 440 hertz, and then we're going to increase, actually we're going to increase linearly the strength of each of these harmonics up to the 9th harmonic. Here's the picture of the wave, a little bit different than the previous one, but again we have a dominant period at 2.27 milliseconds. Okay, you heard the first tone was of this wave with the increasing power in the higher harmonics, and the second was the complex built-up wave that had decreasing power at the higher harmonics, and then the last tone was the first signal, which is the pure sinusoid. You can see this one, because it has increasing power at the higher harmonics, is even tinier than the second one. Here's the two wave shapes in time. Here's the one that we talked about that had decreasing power in the higher harmonics. Here's the one that had increasing power in the higher harmonics. Both of them show this dominant period. Now here is the line spectrum and the cumulative line spectrum of this most recent signal, the one that has increasing power at higher frequencies. And you can see the powers go up with frequency, and the step sizes increase in the cumulative line spectrum. Here's the spectral centroid, which now is 3126 hertz, and it's over at this end of the spectrum because there's more power at the higher end. This is the autocorrelation of the signal that has more power at the higher frequencies. Shows again that the pitch is 440 hertz. And this is the comparison of the two built-up signals. This is the one that has decreasing strength at the higher harmonics. This one has increasing strength at the higher harmonics. This one shows the lines dropping off in power with frequency. This one shows the lines increasing in power with frequency. Here the step sizes decrease as you increase in frequency. Here the step size increases. And here are the two autocorrelations of the two signals. Decreasing harmonic strength, increasing harmonic strength. They both show this period of 2.27 milliseconds, and they're both saying that they have a pitch of 440 hertz. Okay, one last signal. We're going to generate a 440 hertz sine wave inside the computer like we did for the first example. This time I sent the signal out on the speaker of the PC into a sound wave. I collected it at the microphone of a Zoom H2. Then I hooked up a USB cable and read the collected signal, recorded signal, back to the PC, and then I took a look at it via these tools. And here's the result. Okay, here's the spectrum of that collected signal. Once it got back to the computer, you see it has a big peak at 440. And also you see that I'm plotting the signal's power over here in decibels, or dB. It's the logarithm of the regular power that I was using in previous line spectra. So we have this peak at 440, which we would expect. But we also have other peaks at other frequencies. But when we take the cumulative line spectrum, which adds up power and goes across left to right, we only get a big contribution at 440 because these other individual spikes here are slender and isolated and weak. For example, the one here at 120 is down 45 dB. Here's one that's down 40 dB and so forth. So the cumulative line spectrum gives us a feel for what is really important in a line spectrum. And that's the signal after it came back into the computer. It sounds just like the regular 440 hertz signal. And I can hear the West High Band in the background. Okay, that completes our first segment.